Welcome back to week 4 lecture 2 of probability theory with actuarial applications. Today our topic is continuous PDFs, in particular joint continuous distributions. So in the last class we actually studied some discrete models where we studied number of auto claims and number of home claims. In the end we showed that they both are related. What kind of situations will arise when we are studying continuous distributions, or if at all why we should study this continuous distribution. For that, let us take an example of a single fire in a large factory, right. This single event can cause you two related losses. One is a loss to the infrastructure building, and second is the loss to the contents or the inventory that is associated with this particular factory, right. So these two factors need to be studied together, and that is where we need the distribution of joint continuous random variable. So naturally these two are not independent. A large building loss X implies large content loss, and we have to study joint distributions for this. So how will these joint distributions look like? So we are essentially dealing with joint PDFs, which are rate of change of probability, not the actual probabilities. So this, if you keep this in your mind, then we cannot talk about the densities in itself, but if we want to talk about probabilities of single dimensional random variable are nothing but area covered under the curve. So when we move to the two dimensional world, this goes into three dimensional world, and it now becomes the volume under the surface. Okay. So that is the main concept here, and you have to evaluate these integrals properly to get the values. Okay. So in order to evaluate the integrals, first we should ensure that the PDFs have similar structure as we were doing with one variable case. So in order to do that, we need to check the two rules of the game, which is the first one, fxy is greater than or equal to 0 for all xy, and the surface is above the floor, which means the area covered is positive. Okay. And the second is, if you integrate over both the variables, this fxy dx fxy, then you should get 1 as a value, 1 as a answer. Okay. These are similar to what we did in discrete random variables, except for the fact that this fxy may take the value which is greater than 1, which we have demonstrated in univariate case using uniform random variable. So same logic applies here also. So because fxy is not a probability, it is the rate of change of probability. Okay. So if you understand this, then the natural passing over will be to understand what happens to the individual random variables. For that, in discrete random variables, we introduce the notion of marginal PDFs. So this is also same notion will continue. Instead of sum, what we need to do? We need to integrate over the other random variable which we are not interested in. That is all. Other than that, the notion is still similar. So what it turns out to be, marginal PDF, let us say for x, is you integrate out y from this. Okay. And if you want marginal PDF for y, you integrate out x from this particular PDF. That is all. So you will have same marginal PDFs. So this is how you will calculate marginal PDFs. Now that we have understood both concepts are related, let us solve a similar problem which we have solved for one dimensional case, that is estimating the constant c. Okay. So now because it is a joint PDF, the distribution is given over as a surface. Okay. So fxy is c times x plus y, this is a plane, and over the region 0 less than x less than 1, 0 less than y less than 1. How will you evaluate this, right? It is very easy. So for sake of clarity I will do it. So, is fxy greater than or equal to 0? If c is greater than 0, because of this definition x plus y will always be greater than 0, therefore, fxy greater than or equal to 0 is by default satisfied. Now, I have to look at this region. So, what I will do is I will first plot the region, and x plus y is simply the plane. So, if you look at this way, it will be simply a plane. So, I do not have to worry about the area is above the xy plane or not. Okay. So, I will skip drawing because it is very clear in this particular case, and the region is rectangular. So, I do not have to worry about it. So, let us do the integral f x y dx dy, okay, and this particular thing will go from 0 to 1, and this also will go from 0 to 1. What do I expect? I expect the answer to be 1. Okay. So, with this setup I am free to evaluate this integral. So, this integral will be integral from 0 to 1 c x plus y dx dy. But this is a very simple integral. I will simply throw this c out, and if I take this x, then x dx is the only worry. Otherwise, integral over 1 dy is going to be 1. So, I will worry about x dx from 0 to 1. The other integral will integrate itself out. Okay. Similarly, when I look at y, I will worry only about y. So, I am getting y dy. The other integral, which is integral, so let me for completeness write 0 to 1 dx, will evaluate itself to 1. So, I will not write it. So, I got this. Okay. So, then what I will do? I will evaluate this. So, integral x dx will be x square by 2, this is c as is x square by 2 evaluated from 0 to 1 plus y square by 2 evaluated from 0 to 1. Okay. So, when I do this evaluation, what will happen? 1 by 2 will come. So, it is c into 1 by 2 plus 1 by 2, c into 1 by 2 plus 1 by 2. So, then this becomes c into 1 is equal to 1. So, c is equal to 1 in this case. So, what is my PDF then? f x y is equal to x plus y over the region 0 less than x less than 1, 0 less than y less than 1, right, and 0 otherwise. Okay. So, let us see the printed answer whether it matches with our answer. Yeah. So, I have done all the calculations. I have done it in a slightly different manner, but you can understand both are same. Okay. So, we have understood this particular thing is a valid PDF, and we have evaluated c to be equal to 1. Now, let us use this PDF and try to figure out what are the marginal distributions. We have already seen this to be marginal is integrating over x if I want marginal of y, integrating over y if I want marginal of x. Okay. So, let us do that. So, let us find the marginal PDF for fx. So, what should I integrate over? I should integrate over y. Okay. So, if that is clear, it is very easy. You just integrate this over y ranges from 0 to 1, x is constant for me. So, that will contribute to a constant, and y will contribute to y square by 2, which we have already seen, right. So, y square by 2 evaluated from 1 to 0 will be 1 by 2, 0.5, that is all. So, x as it is plus 0.5 will be the answer. So, one sanity check that you can do when you are doing these kind of integrals, you just integrate this f x x dx from minus infinity to infinity and check that whether the sum is coming to 1. If it is coming to 1, the marginal that you have figured out is correct. Okay. Essentially I am checking whether fxy dx dy together is coming to 1 or not, that is all. So, but this is important, this is a sanity check. If you do that, then your life is easy and you are guaranteed that your answer is correct. Okay. Now, in exams they will not leave you with these kind of simple limits, rectangular limits, they will trick in these limits. So, let us take one example of that kind and see how you will escape that trap. Okay. So, now the PDF is given, you are given that this is a constant PDF C uniform. However, the trap is in the region, you have x y less x less than y less than 2. Okay. So, your region is dependent. How will you handle this trap? First thing, you plot, do nothing but plot this xy plane. I was mentioning in earlier example also, you plot this xy plane. So, 1 is x is less than y. So, it is very important to draw a line which is y is equal to x. Okay. So, this is a line, say y is equal to x. Now, where is the region? X is less than y. So, on one side it should be 2, on the other side it should be 2, because that is what the limits are. Okay. So, where is the region? If I select any point over here, does it qualify that x is less than y? Okay, let us say this point is so we will have point which is 1 1 here, right, 1 1. If I take any point here, what will be the value of this point? It will be less than 1, right, and what will be the value of this? It is 1. So, this point definitely does not qualify for this region. Okay. What if I choose a point over here? This point will qualify, that means the region of my interest must be somewhere here. So, once you identify the region correctly, your 80% of the problem is solved. Now, what remains is to make this a valid density. To make it a valid density, what you need to know? The area under the curve should be equal to 1, that is what we will focus on. So, that means this area under the curve should be equal to 1, and that area, what is the area? Half base into height. So, half 2 into 2, this is 2, this is 2, and therefore, I get the answer to be equal to 1 by 2 getting cancelled, 2. Okay. So, this 2 cannot be the area, right, because I want the area to be 1. So, I have to replace this C with 1 by 2, correct, then only this area will become 1. So, let us replace this with 1 by 2, put C to be 1 by 2 and integrate over this region and check whether we are getting the integral to be equal to 1. Okay. So, let us say this integral of fxy dx is half dx dy. I need to be careful because x is trapped between 0 to y and y is from 0 to 2, and this I want the answer, I expect the answer to be equal to 1. Let us verify. Okay. So, this is 0 to y. So, naturally if I am integrating with respect to x, this x by 2 will come and it is evaluated from 0 to y. Integral from 0 to 2 dy will remain as it is. Okay. So, what is this? This will become y by 2 plus 0. So, it will be integral over 0 to 2 y by 2 dy. So, this will again become 1 by 2 will be thrown out and this is y square by 2. So, this will become So, what is y square from 0 to 2? What is y square? Y square will be 4 upon 2 into this half minus 0. So, that gives me 4 by 4, which is 1. So, the answer is 1. That means this C is equal to half is the correct answer. Okay. So, I got the answer to be C is equal to half. So, I have done the sanity check and I got this answer. Okay. So, that is one way. I have also shown you the validation through integral way. So, you can actually integrate, you can actually find out this C using that integral also. So, if f(x(y) is equal to half on 0 less than x less than y less than 2, the same area, the same PMF, now you are asked to find probability of x greater than 1. So, the problem can be a dual problem. You are given C and then you are asked to find probability of x less than 1. How will you find that? Again, you can do it in two ways. First way is the geometric way, but it may ditch you sometimes, or it may not be accurate sometimes, but in this case it becomes accurate. You just look at the vertices of your triangle, which we have drawn in the last slide, and those vertices are 1 1, 1 2 and 2 2, and you calculate the base and height of that triangle where x is greater than or equal to 1, right, and that height, that area comes out to be 0.5, and then you have area into height of that PDF that you multiply, you get the answer to be 0.25. So, probability that x less than 1 will be actually 1 minus this 0.25, which will give you 0.75. Okay. So, this can be an intuitive method when your C is a constant thing. However, the robust method, that method which is safe, is calculus method. You want x to be less than 1, correct. So, you put the limit of x to be less than 1 and y less than x. So, you have to evaluate y trapped between x to 2. Okay. So, that is what you have to do, and that is what you have done here. Y is integrated from x to 2. So, that is the idea, and then it is just a matter of integral. You evaluate this integral, you get the answer to be 3 by 4. Both answers are matching and both answers are correct. However, the fast method can be tricky sometimes if your density is coming in some complex form. Calculus method is a safe method if you have good handle on integrals. Okay. So, this is what you should always look for. So, we have covered a lot now. We have started with continuous density, we have looked at joint density, and we actually evaluated that constant drill, and then we actually figured out how to calculate these probabilities given the joint distribution. So, let us summarize what we have learned in today's class. We have learnt how to model two continuous random variables at the same time. In course, we mastered these tools where we are looking at joint PDF. A probability is the volume under the surface, the joint PDF is the surface in a 3D plane. We also saw the two rules. First, f(x(y) dx dy should be equal to 1, and we solved some problems for finding C. Then we looked at how the integration will happen over a region, and we also designed a way to find the marginals fx or fy both, where our key strategy was always draw a region before you integrate if it is non-rectangular domain. Okay. If it is a rectangular domain, you do not have to worry, you can straight away start with the integral. So, what we will do in the next class? We have already seen these two random variables are interacting with each other. So, it is naturally important to ask a question, what if I know something about one random variable, what will happen to the other random variable. Similar thing we handled when we handled probability of event, and we call that as conditional probability. The next we will look at from joint distributions how to link them to conditional distributions. Given there is a fire claim, what is the probability that there will be a home claim? All these questions can also be answered when you study conditional distributions. In the next class, we will look at these distributions and master the joint distributions altogether. See you in the next class.